Hello, it's Keith here, and this is lesson 2 of my IBM370 assembly programming tutorials. We're looking at the absolutely ancient IBM370 because I enjoy playing with ridiculously old systems and assembly language. So last time we looked at some beginning stuff, some very simple commands. We tried out some little bits with addressing modes, things like that. Now what we're going to do today is we're really going to dive into the addressing modes. I like as my second lesson in each of my assembly tutorials to go through every single addressing mode one by one and with examples, so that you've got a sort of reference point to go back to if you forget which ones are available or how they work. That's what we're going to do today. We're going to be trying out all the addressing modes. Now we're going to have to use some commands that are a little bit confusing and that really we will come to later and discuss in detail, but some of these addressing modes only work with those commands, and so just bear with me on that. As I say, the main focus today is we will see every possible addressing mode available on this system. Okay, well, let's go over to our source code and let's check it out. Okay, so first of all, let's get our server started up. Now, if you missed last time's lesson, please go back and see it, but we're using the Hercules simulator. So first of all, we'll check it starts up okay with this test JCL file. So we use the Hercules job for that JCL file, and if we just start up here, now just on my other screen here, there's some screens starting up. You can just see them off screen there. Now I've got some send key scripts that send various key presses to those, so I'm just leaving them well alone for a moment, and then I'll move them into the frame so you can see them. Although the way I've got things set up, we never actually need to use them. Okay, so there's our dump there. So our server has now started up. Okay, so that is our terminal window there. We'll get that out of the way, we don't need that. And that is our server there, and so we don't need that. We just leave them off screen. We don't. What we look at in these tutorials is the simulated printout, which is this thing. Now, what I suggest you do is if you change the hello world example or whatever example you're running, so that you know that you're not seeing old text, basically, just in case the log file's got a load of junk in it. So I changed this to I like IBM here, and if we look at our file here, you can see I like IBM. So our server's definitely running. We're not seeing old information here. This dump here, I've basically written some .NET programs that basically tail the file, and one looks just for error messages, that's that one there, and one sort of basically tails the file and shows the new part of the file, but occasionally they glitch out, so that's why we ran that test and showed that message there. Okay, so we're going to use lesson2.asm. At the start of our code, we've got some branches to the various sections. So the star at the start is the comment, so we remove that star. The semicolon isn't a comment. The sole reason I've put the semicolons in is because that is what Notepad++ thinks is a comment for ASM files, so it colors them nicely if I include it, but it's the star doing all of the commenting work there. So we're going to run the first example address addr reg here, and if we just now run not with Hercules job, because we've not got a full job file, we've only got a partial file. So we use basic head and foot, which includes my header and footer and my debugging tools, like these monitor commands. So we just wait for that. Okay, so now we've got a much smaller output here, and this is just the result of the program we've just executed. Okay, so our first addressing mode is known as register addressing. So this has the sort of official syntax of R1, R2. This is sometimes referred to as RR addressing. These are the sort of terminology within the official IBM documentation. And a register addressing is the absolute simplest in a lot of ways addressing mode. So this is where our destination is a register and our source is a register. The destination is basically always a register, give or take, with the IBM370, except for like storage commands, for example. But generally speaking, the destination is always a register. The source, not so much though. Now, I think it's always the case that if the final letter in the command is an R, the source is a register as well as the destination. For example, what I mean is if we just use the L command, the source would be a memory address, but LR, the source, is a register. And you see a lot of other commands with an R at the end, and they're all using a register as the parameter. So as I say, that's pretty much the rule. In almost all cases, except for save commands, store commands, the parameter on the right of the comma is the source. The parameter on the left of the comma is the destination. So LR R0, R1 is taking the value in R1 and storing it in R0. Okay, now if you look at the output here, you can see here we dumped all of our registers at the start here, and then we dumped them again at the end here. So if we take a look, you can see that R0 contained that value there and R1 contained that value there. but after the execution, the value in R1, that 94FF8, has been transferred to R0. You can see R0 has changed there, and that's because of that first command there. And you can see we've done that in all kinds of cases here. We're even using R13 here. Now, just a sort of reminder, if you're playing about with this yourself, and I would encourage you to do that, I would advise you against changing any of the registers greater than R10. You can do anything you want with those early ones, but some of the registers have special purposes. So basically, the ones you sort of need to avoid using are R15 is used for the subroutine entry point, so often used for calling addresses. R14 is the return address. R13 is the save area, which is effectively like the stack. Now, my programs, the way they're configured, R12 is used for the using command, which we discussed last time. We'll discuss it in a moment again. And R11 is used by my test code as a sort of a pointer to a buffer, a string buffer that I use to build things. When we run commands like monitor 8 here, BAL branch and link is calling monitor 8. The R11 register is used to remember where the characters were drawn within the buffer before the buffer is sent to the screen. So as I say, if you're using my code, you want to stay, you can use anything up to register 10 for whatever you want, but stay away from those other ones because otherwise the program will probably crash. Okay, so anyway, as I say, register, very, very straightforward. Register on the right is the source, register on the left is the destination. I've got the comma in the middle there. Very, very simple addressing mode. Okay, so now we're going to look at this second one here. So this is known as base, index and displacement. Now this is the most common kind of addressing, and I suppose the most important for that reason. This takes a base register, which you will see in the documentation as B2. So this is a register that points to a memory address. You've then got a second register, which is basically an offset to that first address, so that is added to the first one here. And then you've got a displacement, and that is a fixed number. So obviously the values in those registers are used, but the number is a fixed value, like an immediate, or if you will, that is put in the final bytecode. So that never changes, you know, in a loop or anything. It's always the same offset. And then the destination on the left of the comma is a register once again. So here we've got various examples of this. And what we've got here is a very straightforward one. We've got the L command, load, so not a register source this time. The source is this address combination here. So we're loading into register R1, and we are specifying that the base register is R7. So we're loading from the address in R7, and R7 is being loaded with hex val 1. If we have a look, where is hex val 1? Hex val 1 is all the way down here, so it's pointing to that 1, 2, 3, 4, 5, 6, 7, 8. And you can see some various other values here. Now, our first specification is R7 is the base. Now, we should be specifying an index register as X2. Now, I've actually specified a 0 here. Now, I could have specified R0 in the same format as I've done down here. Now, the reason I haven't is R0 has a special purpose. If you specify it as the index register, R0 becomes a hardwired 0. So the value in R0 isn't used. It's the value 0 itself. So effectively neutering that index register. And then finally, we've got our fixed numeric value, a number there, and that is a 0 as well. So basically, all of this lot is simply saying load R1 with the value at the address in R7. And so if we look at our example here, you can see R1 has been loaded with 1, 2, 3, 4, 5, 6, 7, 8. And as I say, that is the value at address hex val 1. And we loaded that address into R7. So all of that is simply loading from the address in R7. And in a lot of cases, we will want to simply do that. We will simply want to load in from a single address register. But there will be times when we want to be a little bit more complicated. So this second time, again, we're not using any index register. So we're just using the address in R7. But this time, we're specifying an offset of 2, and we're loading into the register R2. So this time, we've basically offset by 2 bytes, and so we will load this half of this part here, and then we will load the 4 bytes here as well, and we're loading those into R2. And if we look at R2 here, you can see 5, 6, 7, 8, 9ABC, and so that is exactly what has happened there. Of course, you could change this value to anything you want, and that will work just fine. Now, I say anything you want. The displacement, that sort of numeric immediate value, has to be 12 bits, and it has to be unsigned, so it can't be extremely large, and it can't be before the address we're specifying. So, for example, I can't load from this address here by using an offset. That is before, and that cannot be negative, so that wouldn't work. Now, in those cases, you see we've used this sort of immediate, offset, displacement, and the base register, and we've not used any index register. You will actually sort of see that this is being used in cases that you may not think. For example, here we've loaded the register R6 with the immediate full 32-bit value 3 here. But the question is, how does the assembler actually do that? There is no command, there's no addressing mode that loads an immediate 32-bit value into a register. It can't compile it. What the assembler actually does is it loads that at the LT.org. So the assembler works out that we want to store the 32-bit value 3 into that register. It stores it at the LT.org, and it calculates the relative displacement from the position in the code around here to that LT.org, and it uses a special register to do that. It needs one of the registers to point to this area of the code, and the way we tell it what register to use is with this using command. So this using command is saying use R12 for your register calculation, and if you remember I said before, R12 is being used for using, and so when we specify something like this, it will actually load from the register R12 here, a 0 here, and then it will calculate the immediate offset to the appropriate part of LT.org. You don't need to worry about that though. It's important to understand that, if for no other reason than to leave the using command alone, and remember to put enough LT.orgs in your code that the displacement doesn't become so great that it goes over 12 bits, otherwise you'll get assembler errors. So just something to bear in mind there. Anyway, what we're doing here is we're loading R6 with the value 3, and then we are going to load R3 with the value at address R7 plus R6. So what the processor is basically going to do is going to take the value in R7, add the value in R6, and use those two together as the address. So we've got the value 3 in R6, and we're going to be loading once again from this area here. So we're going to effectively offset by 3 bytes. And so one would expect we'll probably load 7, 8, 9A, B, C, D, E. Well, let's see what actually happened. Well, here's the loading of R3, and if we look at R3 here, you can see 7, 8, 9A, B, C, D, E, and so that has loaded as we would expect from that calculation. Now, just to make the point I said before about R0, when we specified the 0 here, that was actually R0, but R0 is treated as a hardwired 0 here. But just to make that point, we're now going to try and do the same thing with R0, and it won't work. Or at least it won't work as we expected. So we're loading R0 with the value 3. So we're trying to use R0 as an index with R7 here. And we think we are, and we're going to load it into R4. But when we look at R4, it's actually loaded with 1, 2, 3, 4, 5, 6, 7, 8. Effectively with an index and a displacement of 0. Because as I say before, it does not matter what R0 is as a register. The index is always going to be a hardwired 0. And for that reason, it's only really these addressing modes where R0 has a special purpose, but in a lot of cases you're probably best avoiding using R0 for things just because you might get confused. You know, if you're just starting out, use R1 to R10 for most of your work so that you don't end up getting caught out by that, because I have on the PowerPC that kind of thing caught me out quite a bit in the early days. So there we go. Okay, now in that case, as I say, specifying R0, R7 here is effectively exactly the same as this line below, specifying 0, R7. But the other thing is we can actually completely omit that index register altogether. So this third example here, we've specified the displacement of 0, but we've not specified that index at all. And you can see here that R4 and R5 are indeed loaded with the exact same value here. It really doesn't matter which one of these we use. Now, just one point to bear in mind though is if we try and take out that displacement altogether and we run again, Well, you can see we've now actually got an error. We do have to, even though we don't have to specify that in that index register of 0 here, or R0 there, we do have to specify a displacement of 0 if we want to do that. So that's just something to bear in mind. Now, finally here, just sort of describing in more detail, and so basically whenever we are loading in a value that is, in this case we're loading an address, but this is a 32-bit address here, and so what this is doing is it's effectively calculating this as an offset to R12, and again it's using R12 because we specified the using command at the top here. And just as reference, this command here, a little bit too complex for this stage, but basically this is loading R12 with the address of the current line of code at runtime, so that R12 contains the value that we've told the assembler it has. So this is telling the assembler to use the R12 register, and this is loading the R12 register in the processor with the correct value that the assembler is expecting it to have. So those two commands are doing that for us. Okay, so that's the most common kind of addressing mode that we will be using even if we don't know it. Now, commands like this might look like we're loading an immediate value of 3, but as I say, it's actually been converted by the assembler to a memory load from the LT.org memory address. We do have a small number of commands that do actually use immediate values, so we're going to look at them right now. Basically, all of the commands on this processor are assembled to 32 bits, and so for that reason it's not possible to load a 32-bit immediate value, but we do have some commands that can work with single byte values. So if we try these out here, we will see them. Now, unlike most of the commands, as I say, in most cases the destination is a register, but these commands working with immediates, they actually load straight to a memory address. The memory address is in a different, more simple format. There's no index register, so basically we've got the base register, we've got the displacement numeric value, the sort of immediate value if you will, and then we've got an immediate value here which has to be just 8 bits. Now, we're going to be using the memdump routine to show the results to the screen, and we're initially loading these values into the test memory here. So if we fire this up, let's see what actually happens. Okay, so first of all, we've moved the immediate value 255 single byte into the address in R8 with an offset of 0 bytes here. And so we've loaded R8 with the value hex value 3, that is our test data, and we've dumped that to the screen. You can see the beforehand test data here, and the bottom version is the changed version. So 255 is FF in hexadecimal, that's what's been shown here. And you can see that first byte has been changed to FF because of that command there. Now, the next command, we used an offset of 12 bytes, and we loaded the value 128, which is 80 in hexadecimal. Now, if we look further along, we can see that there has been loaded with the equivalent of 128. And then finally, we loaded the value 15 into offset 15 here, and that is 0F, and you can see that just here. So there we go, that's that 0F there. Now, there is some limitations here. As I say, 0 to 255 is fine. We can't load signed numbers, so we can't do sign extension or anything, so we can't load a 32-bit value of -1 or anything. Now, ironically, of course, if it's a single byte, -1 is actually the same thing as 255, but as I say, the assembler won't accept that, so we do have to use an immediate value of 0 to 255. Now here we've used the move immediate command. There are some other commands, like there are some logical operations which will use an unsigned immediate as well, but it's in the same basic format as these. As I say, we're looking at the addressing mode, not every command that supports them. But say that's the immediates. And as I say, anything larger than a single byte, we would need to specify with the equals and with some kind of type definition. And as I say, they are actually not immediates. They are loaded at the literal org. So now what we're going to do is we're going to look at a more complex addressing mode, and there's relatively few that use this. This basically has two register specifications, which you'll see in the documentation as R1 and R3, and then it has a base register and a sort of an immediate displacement numeric value. Again, no index register offset, so just the one register and the one numeric value there. But this takes two registers, and the most sort of the time you're going to see this most is with the load multiple command and store multiple, and these are in a lot of cases used to simulate a stack. It's called the save area on this system. We're going to look at it next time in more detail, but at this point again, we're just going to see this command so that we see the structure of the registers and the syntax of the addressing mode. And so we've got two examples we're doing here. We're using the load multiple command. Now this will load a sequence of registers from a specified address, and so R0 and R3 specify a range of registers. So R0, R3 means R0, R1, R2, R3. We're loading them from the address in R7 plus an offset of 0. And I've dumped the data to the screen. We'll be effectively loading from this test data here, but you can see it on screen here. And so when we load R0, R3, and then R7 here with the offset of 0, we are effectively going to load these bytes here into the first 4 registers. And you can see R0 contains 1, 2, 3, 4, 5, 6, 7, 8. And then R1 contains 9, A, B, C, D, E, F. R2 contains 1, and R3 contains 2. And that is effectively loaded 4 32-bit values from here as a sequence there, because of that R7 with the offset, the displacement of 0 there. Now the second time we're loading just 2 registers, mainly because we haven't got much data left, when we're loading from an offset of 8 bytes, again using R7 as the base there. And so 8 bytes long, we'll load from this 32-bit value with just 1 in it and this 32-bit value with just 2 in it. And of course we've loaded into registers R4 and R5, and you can see R4 and R5 do contain 1 and 2 there. So that is, as I say, in a lot of cases is the most common use of register and base and displacement in this syntax here. There is a rather strange example of this addressing mode, technically speaking, and this is the shift commands. Now, this, you can see here we've got a register, and we've got another register, and we've got a displacement. And you might think, well, that isn't the same command and syntax, you know, we've not got the same addressing mode, we're missing a register here. Technically, well, technically you're wrong, actually. I mean, logically you're completely correct, but if you look at the documentation of the processor and how these commands actually assemble to bytecode, technically speaking, this is using the same syntax. The other weird thing about this command is this might look like an address specification using R6 with an offset of 6, but that's not actually what happens. R6 we've loaded with the value 2, and this 6 is added to the value in R6, but this is not used as a source address. That resulting calculation is used as a shift amount. So what this is actually doing is effectively shifting the 64 bits at R4 by 6 plus the value in R6, so 2, so by 8. And so if we look at our 64-bit value in R4 and R5 here, it's effectively shifted 8 bits from its previous value here. And the reason for that is that we took the value in R6 of 2 and the displacement value of 6, added them together, that became 8. And then we shifted out the value in R4 by that 8. As I say, it sounds completely wrong that I'm mentioning it in this section, but if you look at the documentation, this is technically register displacement. They've kind of misused the addressing mode, if you will. So that's why I've mentioned it here, even though it looks like it should be mentioned somewhere completely different. And again, I understand that I'm not really covering these commands in a lot of detail. We're not discussing these commands at this stage. We're discussing the addressing modes. We're coming back to the commands in a later lesson, so we'll see them in far more detail then. As I say, this is really one for completeness, so that we can say we've seen every addressing mode available on this system. Now, the next one we're going to look at is sized. So this is another one that's a little bit odd, shall we say. So basically, we're getting a bit confusing here because so many of these look similar. So basically, we're specifying a displacement, an immediate displacement. We're specifying a register that has a memory address. So this is going to use the value in R7 plus 4 as an address. And then what we've got here is R7, and we've got 8. So this is the address in R7 plus 8. But then we've got this 4 here, and you might think, oh well, that 4 is obviously specifying R4 as an index, but you're wrong, because in this case this is a length. So we're specifying that basically this is the move character command. The C in MVC, move character, means bytes. Bytes are referred to as characters in a lot of cases on this system. So we're saying basically transfer 4 bytes from R7 with a displacement of 4 to R7 with a displacement of 8. The 4 here is not a register specification or an index register specification. It is an actual number of bytes, a length, if you will. So if we run this here, we're dumping hex value 5 to the screen a couple of times. So here is the starting position here. And then after we've done that copy of 4 bytes from offset 4 to offset 8 here, you can see basically that 9A, B, C, D, E, F, 0 has been copied there. Just for clarity, let's change it. Let's change that 4 to a 6 and let's run it again, because as I say, maybe it's a little bit confusing having 2 4s in there. So let's try it again. And this time we're specifying a length of 6. And so if we look again, well, this time you can see we've copied 9A, B, C, D, E, F, 0, and then we've actually copied 2 of the bytes again, 9A, B, C, because of course we've now wrapped around. We copied the first 4 bytes there, but then we started copying the range we just copied, and we copied the 9A, B, C from there. So again, as I say, this is the destination address calculation. The R7 and the 8 here is the source address calculation, and the number here, the 6 in this case, is actually the length, the L here in this. This is the official syntax of this command. Now, in this example here, we've specified our addresses using registers and displacements, but if we want, we can use labels. So here we've specified them as 2 labels, and in that case, the syntax for this assembler, we actually specify the length in brackets after one of the labels here. So here we are copying 3 bytes from hex val 5 to hex val 6. Now hex val 6, here you can see, is the last part here, and we are copying 3 bytes here. And so if we have a look at this case here, you can see we've copied 1, 2, 3, 4, 5, 6 down to here. So that's what we've done there. We can even be more clever here. What we've done this time is we've specified a symbol. We've defined lendef as equal to 4, and then we've specified lendef in brackets here, and hex val 6 we're using again, but this time we're adding a sort of immediate of 8, and of course it's going to be the assembler that's going to calculate that. And so in that case we've copied the 4 bytes to that address down there. Again, just something to bear in mind, and I haven't maybe made it clear this time, but officially this assembler does not require you to specify registers as R7. You could just specify these as just 7. So if we the R's are symbols that I've defined. So the R7 is a symbol I've defined to just contain the value 7, but actually this would have compiled just fine in that mode. And the reason that I specify the R's there is because otherwise it gets very confusing as to which is a register specification and which is a displacement, and which is a length and things like that. So as I say, I personally think it's essential to specify the R's for my sanity and for hopefully for you to learn this. I guess if you were typing this in using punch cards, which is apparently how this system used to be programmed, I guess you would be desperately avoiding that extra punching, but for us that's not a concern. Now that example used a single length specification. Now what we're going to do this time is we're going to use 2 specifications, so 2 lengths. So this time we have L1 and we have L2. What we're going to do here is we're going to use the zap command, which doesn't fire laser beams anywhere or anything. What it does is it's effectively a way of copying binary coded decimal from one place to a different place where the source and destination are different sizes. It effectively adds to 0, which is why it's called add packed. Binary coded decimal is something we're going to come back to later. I think it's lesson 6 we cover that. So again, I'm not going to go into the details of the command particularly here. The point I'm making is 2 lengths here, so 8 and 4 here. And so what this is going to do is it's going to copy the 4 bytes from this source after the comma, 4 because of this 4 here, that's the length of the source, offset of 0, and the base register is R7 again, and we're going to copy to the destination, and the destination is register R6, although actually I've loaded them both with the same value, so we could have used R7 again there. And we are going to transfer to a destination of 8 bytes, so we've doubled the length here, effectively making the field bigger, if you will. And we're using an offset of 16 here. And so if we run this example, we will see this in action. Okay, so there is our source data before we made any changes. That's the memory dump there. But then afterwards, you can see that that bottom line used to contain all Fs. But then afterwards, we've copied our 4-byte value, 1, 2, 3, 4, 5, 6, 7, C. And this has now become a load of zeros and then 1, 2, 3, 4, 5, 6, 7, C. And that's why it's called zero add packed. The zero, it's been added to an 8-byte zero value, basically. Now, this is binary coded decimal. And just as a sort of teaser for the final lesson, the C here is actually a sign. So that's not a digit. What we've effectively got here is plus 1, 2, 3, 4, 5, 6, 7, if my memory serves me correct. So that's what we've got there. And as I say, the point I'm making is, again, we've got two address registers here. Now, in that case, we were specifying R7 and R6 here, but we could have actually used R7 for both. It does still work just fine there. But again, as I say, the point is we have two length specifications. And again, just to be clear, by no means am I showing you every command that has these addressing modes. It's just the point I'm making is, once again, just to show you an example of each addressing mode, so that later when we come back to them, if you are struggling to remember the syntax of an addressing mode, you can see them all here in a single lesson. Of course, you can go to my website and there's like a really simple table here on the front page that shows them all in a nice list with some of the examples we've seen here and with a breakdown of the things. And as I say, these are the formats as you will see them described in the official documentation, and this is the syntax you will see in the official documentation. So don't blame me for why there's an R3 and no R2 and things, because as I say, that's simply how the official documentation is. And in my experience, it's always best to use the official documentation terminology, because you probably want to go back to the official documentation from time to time to double check how commands work and things. Anyway, I hope you've enjoyed what you've seen. IBM370, of course, a very complex system. If you're looking for something simpler and something more modern and relevant, I've got tutorials on every processor out there really for assembly these days. Z86, 502, 68000, 8086, ARM, all that kind of thing. I also have 2 books covering a wide range of processors and things as well. You can buy them on Amazon in print. And so as to say, if IBM370 is looking a bit complex and a bit useless because it's so old, I fully understand that. I just I do it for fun, and as I say, I enjoy reminiscing and generally being impressed about how powerful these ancient systems are. As I say, the IBM 370 came out in the 1970s, I think 1970 itself, which is before I was born, but it certainly taught me a thing or two. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.